Hello, I'm Andrew. I'll be presenting my final year project titled Dielectric and Ionic Screening in Ligand-Capped Gold Nanoparticle Arrays under Aqueous Exposure. My project focused on how gold nanoparticles, which are widely used in biosensing, behave when placed in aqueous environments, particularly salty solutions. This is an important question because biological and physiological environments are inherently full of water and dissolved ions. Let's begin with a quick rundown of what to expect in this presentation. I'll start with the background and the motivation for this project, where I'll explain the role of gold nanoparticle arrays in biosensing and why it's important to understand how they behave in biological environments. Then, I'll move on to the experiment, briefly covering how I synthesize the AUMP arrays, and then how I characterize their electrical behavior in air, water, and salt solutions. Following this, I'll address two key questions. How did the AUMPs behave in the aqueous solutions? And did introducing ions change anything? If so, how? Finally, I'll wrap up with the conclusions and future work where I'll reflect on what this could mean for electrochemical transducing in biosensing applications and what the next steps might be. So what is a biosensor? Well, as the name suggests, it's a sensor that detects something biological. In practice, this means it senses the presence of a biological molecule, like glucose, a virus, or a protein. And the role of the biosensor is to provide a measurable output with meaningful information, such as what your blood glucose levels are, or whether you have a viral infection. But how do biosensors do this? Well, a biosensor consists of three essential elements. First, there's a biorecognition element, also known as the bioreceptor. This is the part that interacts directly with the biological target, otherwise called an analyte. It could be an antibody, an enzyme, DNA, or even whole cells. Bioreceptors are then functionalized to a transducer. This is the element of the biosensor that converts biological recognition events into a physical signal. These signals could be electrochemical, optical, or piezoelectric. However, signals alone don't tell us much, and that's where the signal processing element comes in. This amplifies and processes raw signals, turning them into a readable output, like a numerical glucose concentration on a diabetic blood monitor. But what does this have to do with AUMPs? Well, they're commonly used as transducers in biosensing, mainly as optical transducers. However, in this project, I wanted to see how they behave before functionalization with bioreceptors in aqueous mediums and get a sense of how their electrical properties are affected by the presence of water and ions. So why are AUMP arrays particularly useful as transducers in biosensors? Well, there are many reasons, but to name a few important ones, they have a high surface to volume ratio. This means you can attach a dense layer of bioreceptors onto them, increasing the number of potential binding sites and boosting detection sensitivity. They are biocompatible, meaning that gold is chemically inert and non-toxic in biological environments, so it can safely interact with biological molecules without causing any havoc. They are scalable, the main reason being that you can use self-assembly techniques at relatively low cost, which is crucial for making practical devices. AUMPs rely on thiol gold binding. This is the chemistry that allows you to cap AUMPs with organic molecules and control the spacing between particles precisely. As you'll soon see, these insulating ligand junctions play a very important role. And finally, they are highly sensitive. Their conductance is governed by something called sequential electron tunneling, which responds to tiny changes in the local environment of these junctions. This, in particular, is what makes AUMPs an excellent choice for transducing biological events into measurable signals. Now, let's look more closely at sequential tunneling, as this is very important, and how this gives AUMPs a unique method for charge transport that is useful in sensing. So each gold nanoparticle is separated by insulating ligands, such as carbon chains. This means there is no continuous metallic path for electrons to flow. So instead, electrons had to quantum tunnel through the potential energy barriers created by these ligands. This is called sequential tunneling, and I've attempted to illustrate this above. The likelihood of electrons tunneling depends on two key factors. The width of the barrier, denoted by d, which is the physical distance between particles, and this can be set by the length of the ligand, and the height, phi, which is the energy difference between the Fermi level of gold and the lowest unoccupied molecular orbital of the ligand shell. The overall conductance of the array thus follows the exponential relationship derived from the tunneling probability of the electrons in this specific system. Zeta is known as the tunneling decay constant, but most importantly, it contains the barrier height dependence of the conductance for a specific nanoparticle array. This equation is particularly relevant to the project as it gives us a way to decipher how changes to a junction can directly impact the overall electrical behavior of AUMP arrays. So let's get into the experiment. The first part of the experiment required me to fabricate ligand-capped AUMP samples, which could then be used to test their electrical properties. I've condensed the synthesis into 3 steps for the purposes of this presentation, but there were many more steps to this. First, we had to synthesize octane-thiol and dodecane-thiol ligand-capped AUMPs using a phase exchange method. This involved reducing gold salts in water and transferring the nanoparticles into organic solvent where the thiol ligands bound to the surfaces of the nanoparticles. To create the arrays, we used a drop casting technique whereby the nanoparticles self-assembled into closely packed monolayers, if done correctly. The capped AUMPs were then transferred to glass IDEs using a PDMS stamp. I then had to determine the charge transport mechanism in air before introducing any liquids by applying a voltage sweep and then taking the IV traces of every device. And by device, I mean an electrode pair that are bridged with the AUMPs. You can see the representative IV traces from the devices I fabricated, focusing on suspected monolayer regions, and I say suspected because I was unable to image them and confirm their morphology. Both the AUMPC8 and AUMPC12 arrays showed smooth symmetric curves centered around 0. This is typical of sequential tunneling and indicates the devices were working as intended. For the C8 devices, which have shorter ligands, I measured currents around plus or minus 1 microamp. Then for the C12 devices with longer ligands, the currents were much lower, around plus or minus 10 nanoamps. This fits exactly with what I expected. The resistance increases exponentially with increasing ligand length, following the relationship for conductance I showed you earlier. And so these results confirmed that the AUMP arrays were successfully fabricated, which is crucial for the next set of the experiments, where the devices were then characterized in aqueous environments to mimic the kinds of conditions these devices would face in real biological systems. I gathered voltage time traces by applying a constant current bias of 0.1 microamps for 150 seconds and recorded the resulting voltage, setting the devices first in air to gather the baseline references, followed by deionized water exposure, and then lithium chloride at 4 concentrations, 0.1, 0.5, 1 and 2 moles per litre. For each test, I applied a 2 microliter droplet onto the devices using a calibrated pipette by hand. This allowed me to probe how both pure water and varying ionic strengths affect the electronic behavior of AUMP monolayers. So let's look at the results. First of all, I'm going to show you the voltage time traces collected under deionized water, 0.1 and 0.5 molar solutions of lithium chloride. In all these cases, I observed an instantaneous voltage drop as soon as the current bias was applied. The voltage dropped by about 4 orders of magnitude compared to the baseline air measurements, reflecting a massive decrease in resistance. Importantly, these aqueous traces remained stable over time, with no signs of time-dependent behavior. But what could cause this? I believe an explanation for this could come from the high permittivity of water driving dielectric screening. As water has a very high dielectric constant, around 80 in comparison to 1 in air, I believe it's plausible that the drop in voltage comes from the rapid reorientation of water molecules, which reduces the tunneling barrier height between nanoparticles. This could increase the tunneling probability, which in turn raises the conductance of the array, exactly as shown by the sequential tunneling charge transport mechanism I showed you earlier. A justification for this interpretation could come from Chen et al., who investigated intrinsic dielectric modifications within an organic molecule placed between 2 electrodes. Though this is not the same system, I believe it can explain external modifications to the dielectric environment. Now you'll see why I separated these results. You can see that at higher salt concentrations, 1 molar and 2 molar lithium chloride solutions, the electrical behavior changed drastically with what appears to be a clear transition from lower ionic concentrations to higher concentrations. Here, the voltage dropped gradually over time, rather than stabilizing instantly as with the lower concentrations in deionized water. Additionally, the total voltage drop was much smaller, only about one order of magnitude lower than the corresponding air traces. And in an attempt to further understand these decaying behaviors, I used a double exponential fit, which is a model I found was commonly applied to systems forming electric double layers. As I just hinted to, I believe what's happening at higher concentrations is that ions are reorganizing at the NUMP electrolyte interface. They form an EDL that acts like a capacitor, gradually screening the electric field and lowering the tunneling barrier over time. Again, the barrier decreases and the conductance increases, but this time it unfolds over tens of seconds. One justification for this view comes from Asano et al., who showed that ultra-thin gold films in electrolytes exhibited time-dependent changes in conductivity due to EDL formation. So let's go back a bit and zoom down to the nanoscale and walk through what might be happening under dielectric screening in deionized water. When I apply a current bias, it creates an electric field across the AUMP ligand junctions. The surrounding water molecules, which are highly polar, reorientate their dipoles to align with this field. These aligned dipoles likely generate a local counterfield that partially cancels the applied field, lowering the tunneling barrier between nanoparticles. This immediately increases the tunneling probability and thus the overall conductance. And because water's permittivity is both high and stable, this screening effect happens rapidly and remains steady over time, which explains why the voltage time traces in water were stable. And when we introduce low concentrations of lithium chloride, the situation ends up looking similar to pure water. At these low concentrations, we have lithium and chloride ions present. What will come to be more important in higher concentrations is that each ion is surrounded by a hydration shell, which is a tightly bound layer of water molecules. These hydration shells restrict the motion of water molecules close to the ions because of ion-dipole interactions, meaning that they can't reorientate as freely under the applied electric fields. However, the bulk water molecules, the ones outside the hydration shells, remain free to reorientate and continue driving dielectric screening. As a result, the overall screening effect at low lithium chloride concentrations remains similar to what we see in deionized water, with an immediate voltage drop and no time-dependent behavior. Now, as we know, at high lithium chloride concentrations, the situation changes and the screening mechanism likely switches to an EDL-driven ionic screening. Here's what I think happens. The applied electric field attracts lithium ions to the AUMP electrolyte interface, forming a compact stern layer. Chloride ions are repelled away from the AUMPs, forming a more diffuse layer further away. This is described by the Stern model, and together these layers make up the EDL, which behaves as a capacitor, gradually screening the electric field across the junctions. With more hydration shells present, the bulk water molecules can't reorientate as freely, reducing the effects of dielectric screening. Instead, the system now operates on ionic rearrangement, and this is why we see a slower time-dependent increase in conductance, as the EDL progressively lowers the tunneling barrier over time. Now, of course, there were several limitations in this project. The first was device variability, followed by lack of imaging, and lastly, irreversible contamination. Now I'll begin to wrap up. It appears I may have identified two distinct screening mechanisms acting on AUMP junctions in aqueous environments. At low ionic strengths, permittivity-driven dielectric screening dominated, driven by the rapid reorientation of water dipoles. Then at higher ionic strengths, ionic screening took over, and this was likely driven by the gradual formation of electric double layers. This is a potentially helpful result, as AUMPC8 seems to be inherently sensitive to ionic concentration, even before any functionalization. This suggests that they could act as threshold-based ionic sensors, detecting when ionic strength crosses a certain limit, such as sensing electrolyte imbalances. But this sensitivity may be a double-edged sword. Biological fluids always contain water and salts, meaning there is a risk that background screening effects could mask the signals from the actual analytes you may want to detect. While dielectric effects from water might be easier to calibrate for, the more complex time-dependent ionic screening may be much harder to correct. This challenge opens up important questions for future work, starting with testing a denser range of lithium chloride. Then I would investigate more electrolytes and ligand lengths. I would image the arrays, and finally I would functionalize the AUMP arrays with bioreceptors to test how well they perform as actual transducers under the influence of the screening effects found in this project. Thank you very much, and I look forward to seeing you.